This is a sort of impromptu stream in celebration, let's say, of the fact that I feel like I finally got in my head, well, full enough for me, understanding of conformal geometric algebra. I'm going to give a sort of taxonomy of the different objects that you see in conformal geometric algebra, like the ones that you can see on the screen right now. It's kind of at the boundary of what I feel like I can visualize. This should be understandable without too much background in conformal geometric algebra at the same time, though. You've got the 1 vectors in red, E1, E2, E2, E3, E4, no, do you know what? So these you'll be very familiar with, I hope. In conformal geometric algebra we have, and I'm going to use the notation E plus and E minus. And if you don't like that, well, I'm sorry, it's really necessary. Oops, sorry about that. It's really necessary because I've got a bit of a cold, by the way, so I'm not very nice to listen to, but you really need to use E plus and E minus in this context because we're going to be shifting between 3D CGA, 2D CGA, 1D CGA. People don't usually talk about 1D CGA. 3D CGA has the signature 4, 1. So 2D CGA has the signature 3, 1, 0, 0. And then 1D CGA, no prizes for guessing, it's 2, 1, 0. 3D is for modeling 3D space, 2D is for modeling 2D space, 1D is for modeling 1D space, and they've all got an E plus and an E minus. This is 3D CGA that I've started writing down here. 2D CGA would just have E1, E2, E plus and E minus. Blah, blah, blah. Yeah, you get the picture. Going to have to move fast here. So you've got E plus and E minus. You've got, let's go down here now. You've got 2 vectors. Or bivectors, if you will. E1, 2, E2, 3. Going to have to do all of them. E3, 1, E plus 1, E plus 2, E plus... No, do you know what? I'm going to adopt the convention that the... I usually do this, so I put those at the end. I'm tempted to do it the other way around. 1 plus E2 plus... But that's a temptation coming from projective geometric algebra. And projective geometric algebra is very relevant to what I'll be saying, but because projective geometric algebra is a sub-algebra of conformal geometric algebra. Everything you can do in projective geometric algebra, you can do in conformal. Okay, E1 minus, E2 minus, E3 minus, and E plus minus, and that's all of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, 10 bivectors, 2 vectors. I'm writing down the algebra. The point of this is that it's easy enough to write down the algebra of conformal geometric algebra, or you can list all of the objects that are in it. But like in a list where you're using writing and symbols, it's another thing to visualize what these things look like. So say that again, people do algebra with CGA every day, but I don't think people are usually thinking about what the things look like. Now, I'm not going to do all of the 3 vectors, but just to give you some idea, it's got 3 vectors as well. E1, 2, 3, E plus 1, 2, E minus 2, 3, etc., etc. All the combinations of that. And then it's got, the quad vectors as well. 4 vectors, and there's at least fewer of these. So E 2, 3 plus minus E 1, 3 plus minus E 1, 2 plus minus E1, 2, 3 plus and E1, 2, 3 minus. Yeah, like I say, got a cold, and that's why I kind of feel justified doing whatever the hell I like today, because this is very academic, so I think it's pretty academic. Maybe it'll be useful to me at some point. And then you only have one 5 vector, which we're not going to think about very much, so I'll just do it in black. 5 vector. E1, 2, 3 plus minus. And then you've also got the scalar. Scalar. Which just looks like... What's the basis scalar? The basis scalar in answer to that question is 1. It's the number 1. Alright. Let's start with the 1 vectors. What do these look like? Well, here's a 1 vector, E1. No, E1 looks like this. It's a planar reflection. And if you're a person... Now, the place I'm heading with this is that sometimes people do CGA. The term is there's direct CGA and dual CGA. And what I'm talking about today is a way that fuses both of them. Because we're kind of trying to follow the sorts of principles that you get from, PGA. Because in PGA, the thing that you've got to do if you want to visualize a thing is to set a bit of algebra. You say, when I'm doing algebra with this thing, say it's E1, what is the transformation that it appears to encode on the algebraic objects that I'm thinking about? And it turns out that E1 does planar reflection. It really does. So, and because it does planar reflection in a particular plane, we visualize it with a plane. Yeah, so here we go. Yeah, it's that plane, and then if you do PGA, then these will be super duper familiar to you. You'll even be like, aren't you just describing PGA? So we've got these 2 planes, and you can ask the question, where do they intersect? And the answer is that they intersect in this line. And I can draw this line in blue, because hooray, these 2 planes. Sorry, I haven't actually said what that plane is. That plane is E1, and this plane is E2. Can you see all of this? Yes, you can. All right, there's E1 and there's E2. We've skipped straight to doing some lines. So this guy is E12. E12. And it's a 180 degree turn, and we're going to put some markup on these things. What do I mean markup? Some extra little annotations that tell you a little bit more about what kind of object these things are. So this plane E1 that we started with, it's got little tiny arrows on the surface of it. And they're pointing in this direction. They're all pointing in the same direction. They're not pointing in that direction. Oh, no. They're pointing in this direction. If we were to consider minus E1, negative E1, so E1 multiplied by minus 1, then you'd get arrows pointing in this direction. But we're not looking at E minus E1. We're looking at E1. And E2, E2 has got arrows going like this. You might ask, why is it that they're going there? And minus E2 would be arrows going. Minus E2 would be arrows going down, of course. There's no particular reason to choose arrows going up versus arrows going down. You just choose your basis, and you've got to. We're choosing a basis right now, and then you derive things as you go forward. Oh, sorry. There's E12. And E12, because it's made from E1 followed by E2. E12 has also a little bit of markup, and it goes like this. Because E12 is a 180 degree turn, you see. And if you take, say, this arrow here that's on E1, and this arrow here that's on E2, and you join them up, and you go by twice the amount that the angle between them, then you get this one, right? You get this little arrow here. Let's continue you a little bit, and because this, it's not just in one place, it's like that. Alright, so there's E1, E2, and E12, and let's draw. We're going to have to draw lots and lots of... You're going to have to draw the same picture many times, I'm afraid, because otherwise it's going to get horrible to look at. So, here's E1 again, with the the arrow should be implicit, and E plus, all right, which is still a 1 vector. Draw E plus, and it looks like this. It's a sphere. And in particular, it's a sphere that sort of cuts E1. It cuts E2 as well. This is E1 again. This guy is E plus. E plus squares to +1, E minus squares to -1. Sorry, I forgot to say that. And that's why it's called E plus and E minus. And E plus and E minus, the reason that they get plus and minus instead of numbers is because they've kind of been tacked on, like E1, E2, and E3. E3 is going to turn out to be this plane here, but we're not quite there yet. E3, E1, E2, E3 look like planes. E plus looks like a sphere. E minus we'll get to. E minus has been my nemesis for a bit, but we can still say that the intersection of a sphere and a plane is still a bivector and still a circle. So here you go. E1 plus. Yeah, that's E1 plus. E1, as you know, it has like little arrows going on it this way. And E plus has arrows going on it. I could say that they're going outwards, or I could say that they're going inwards. I hope, let's just say that they're going outwards, because that's easier to draw, and I have no other reason than that. It's got these little, this one, no, this one on its surface. So these are arrows sticking out of E plus. And okay, so you can follow the same logic. Can you? Hope so. Yes, you can. Because remember that E1 has little arrows kind of on the inside here. It's got an arrow like that, and then it's got an arrow on the inside of E plus, sorry. So that's another E1 arrow, and these are all E plus, and those are E plus arrows. I guess this would be easier if I was using different colors, but yeah, sorry, it'll have to do. So what we do is we join up this arrow inside. That's an arrow that's an E1 arrow. It's sticking out of E1, which is the plane. And we join it up with this arrow here, which is sticking out of E plus. And we keep going, and we get, look, it's a curvy arrow that's curving around. It's curving around E1 plus. All right. E1 plus. Let's look at a little. So E12 is a 180 degree rotation. E1 plus is, well, it's actually also kind of like a 180 degree rotation. This is a conformal transformation. You're not seeing a circle here, but there is a particular preserved circle that isn't moving in this picture, and this thing is performing a weird kind of rotation around that circle. Ordinary rotations are rotations around lines. This is a rotation around a circle, and E1 plus is the particular case of a 180 degree rotation around a circle, because I want to express to you that you can add things together. You can add our planes together and you will get other planes. A plane plus a plane is always a plane. Sorry, a plane. I mean, we're talking, in the context of CGA, you talk about things called generalized spheres. Goodness me. So what is a generalized sphere? While I colour this in, a generalized sphere is a sphere is an example of a generalized sphere, but a plane is also an example of a generalized sphere, because a plane is a sphere that is very, very big. It's gotten very, very big, and it's ended up infinitely big. Yeah, that's what a plane is. So, you know, here's E1, here's E2, and here is E1 plus E2 plus E2. It might help. Let's go down to 2D CGA for a second. All right, 2D CGA. We're gonna draw a sort of picture frame to remind ourselves that we're thinking about just the world of 2D. We're going to think about the world of 2D a lot. So in 2D CGA, E1 is not a plane, it's a line. And E2 is also not a plane, it's a line. And E plus is not a sphere, it's a circle. That makes sense, doesn't it? E plus. Did I label that correctly? Yeah, E1 plus E2 is not a plane, it's a line. No. E1 plus E2. Alright, I just added E1 and E2. What if I add E1 and E plus? The answer is that you get a sphere. And not just a thing that a weirdo would call a sphere, you get a thing that actually looks like a sphere, a circle in this case. So this is E1 plus E plus. And you can ask the question, what is E1, what is E1 plus? Because, okay, E1 plus E2 is different to E12. E12 is a 2 vector, and E1 plus E2 is still a 1 vector, because it's a sum of 1 vectors, and the sum of 1 vectors is a 1 vector. In 3D CGA, E12 and E1 plus are circles. In 2D CGA, E12 and E1 plus are point pairs, and similarly they've kind of got a markup going like that around them. Or possibly the other way. I've chosen an incompatible combination of arrows, so I'm going to have to yeah, I'm gonna have to erase these little arrows here, and now I can draw E1 plus E2's arrows correctly. So I have drawn those correctly because they have joined up an arrow going like this. Like this arrow with this arrow, right? And that is consistent with this arrow that I drew here. And to review, E12 is a 180 degree turn because if you perform a reflection in E1 followed by a reflection in E2, you get a 180 degree turn around that line. And E1 plus is a 180 degree, something like a rotation around this circle, because if you reflect in E1 and then you perform what's called a sphere inversion in E+, you get that thing. Sphere reflection. Alright, so if you say I reflect the whole world into this, you know, perfectly mirrory like sphere what I've got, then that's a sphere reflection. There you go. There's a nice one. Yeah, beautiful things. And if you perform a reflection like that followed by a planar reflection, you will be performing a 180-degree turn around this sort of circle that you've got hovering in three-dimensional space there. Before we get to anything E minus E, let's say a little bit more about things that we can do just with what we've got so far. Here's E3, and I'm not going to draw the markup. You can try to remember the markup from previous diagrams. E2, 3. And now we're going to draw our first trivector. Our trivector is down here. And it's a point. Or rather, it's a... I've started with not the best one to start with, in a way, but, you know, that is E1, 2, 3. But a slightly better thing to do would be to draw the following. Lots of drawings. Hey, what about E1, 2 plus? Because we've got three whole objects in this picture. The answer is E1, 2 plus is going to be here, but also here. See, it's a point pair. Again, so joined with by a kind of dotted line, but like that dotted line is not a proper part of E1, 2 plus. The thing that you have to stay on top of, which is not easy at first, but not that difficult, and it is a fundamental part of the universe, so you'd better get used to it, is that, you know, in 3D we've got spheres and circles, and a reflection in 3D, well, a planar reflection, a hyperplane reflection in 3D is it's in a plane, and a hyperplane reflection in 2D is in a line. In 3D, lines get involved in like 180 rotations, for example. And circles also can be involved in those 180 rotation things. In 2D, point pairs get involved in 180-degree rotations, and in 2D, circles are involved in reflections. And you build point pairs, that is, rotations, out of lines and circles, whereas in 3D you're building circles out of planes and spheres. Complicated? Yes, but it's part of the geometry, so yeah. Imagine performing a reflection in E1 followed by a reflection in E2 followed by a reflection in E+. Slightly difficult to picture at this stage. I'm afraid it is going to get worse. But yes, if you were to, you can see that is a reflection, and you can say to yourself, hey, look at that point pair that you've got there. Will that point pair at any stage be moved? The answer is no, because E1, if you perform a reflection in E1, that won't move that point pair. If you then perform a reflection in E2, that still won't move that point pair. And then if you perform a reflection in E+, that still won't move that point pair. So E1, 2 plus, if you transform things using E1, 2 plus, you will be doing some kind of thing which keeps these guys in place, and everything else just goes like around it, whatever. We want to have a markup. We want to put a little annotation on E1, 2 plus. It turns out that there's different kinds of line and circle and plane and sphere, and you use markup to distinguish them. You also use the markup to tell whether the thing is E1 or negative E1, or E12 or negative E12. Negative E12 would be with the nope, would be with the arrow going like that. That one would be negative E12. But yeah. So you can reverse markup arrows by multiplying by -1. This one is the same kind of object as this one. They're both trivectors. They're 3 vectors. And you might say, hey, hang on. That guy there is a point pair, whereas this guy here is a single point. Actually, this guy, you might say he's not a single point. He's not a single point because there is another point, which is the point at infinity, and that point at infinity is included inside this point pair in or rather it's included in E123. I'm not saying it's sort of sitting inside of this point or something, but I am saying that it's included there. And now, alright, now it's time to go back to 2D CGA, and we will make that concept more intuitive. Reminder that this is 3D CGA, 2D CGA, and those are, it's really important to distinguish those. I mean, they've certainly got a heck of a lot in common, but in this one, you're saying that E1 is a line, and in this one, you're saying that E1 is a plane. But that's going to get super confusing in a second, because there's a tool that I use to think about 2D CGA, and it's really, really helpful. I don't feel like I can give this explanation without explaining this tool. And this tool is called the hyperbolic view of 2D CGA. What does that mean? Hyperbolic space is... It was discovered about 200 years ago, and it's a qualitatively different kind of way for a universe to function in comparison with the way that you intuit our universe functioning. The way that you intuit our universe functioning, spatially at least, is using Euclidean geometry. And in Euclidean geometry, the angles of a triangle add up to 180 degrees, for example. Maybe you want to look up somebody else's explanation of hyperbolic geometry. There's lots of them out there, because we're going to be having to do somewhat advanced hyperbolic geometry. To say it briefly, we're going to use the Klein disk model of 3D hyperbolic geometry, which actually makes it more like a Klein ball model. We're going to use the Klein ball model of hyperbolic geometry to then to gain insight into 2D geometry. 3D Klein ball, we're going to call it, looks like, we're definitely going to draw it in a different color. It looks like this. It looks like a 3D sphere. And the thing that I like to do, I like to remind myself that it's a sphere by drawing a little plane underneath it in sort of perspective. And now it just kind of immediately looks like a sphere, doesn't it? At least I'd say so. So there's our Klein ball, and if you our Klein ball, and I don't have much to say about this plane here. Like, just think of it as a thing that's there to help you view this as being more spherical for now. The Klein ball allows you to say to yourself, hey, I'm looking at a three-dimensional space now, this space. I'm looking at a three-dimensional space now in which things work very differently to usual. And one way of saying it is that if you're inside the ball, you can't get outside the ball. And if you're outside the ball, you can't get inside the ball. You might say, well, surely there's loads of, like, in ordinary 3D Euclidean space, you can kind of go where you please. Well, if you've got enough energy or whatever. The to get inside the, if this was a Euclidean sphere, assuming that it's not hard, assuming that it was just bounding a region of ordinary space, you could say, well, I could just pick up some object and I just move it by a Euclidean transformation into the sphere. But that is not allowed. Not allowed. It's not like we're playing a game and this is not the rules. Like the this is, well, yes, it is a game and these are the rules that we're playing by. But it's not just some random rule we came up out of nowhere. It's a rule that does drop out of the fact that in hyperbolic space you have that the angles of a triangle do not add up to 180 degrees, etc., etc. So this is going to be the Klein-Ball model of three-dimensional hyperbolic geometry. And let's say some things that are familiar about the way that this thing works. So if I draw, and I'm going to draw it very suggestively, one thing that you might say when you look at this is, oh, hey, this is a sphere. Haven't you just been telling us about spheres? You're drawing loads of spheres on the right over there, and that you told us that was 3D space. Now you've drawn a sphere, and it's over on the left here, but you were telling us this is 2D CGA. Well, this is a qualitatively different kind of sphere than all the spheres that were over there. The spheres that were over there, I drew little arrows on them, but I am not going to draw such things. No siree. This sphere is not even an element of, in itself, this sphere is not even strictly an element of the algebra. It's not like I can say, oh, this is E plus or whatever. No, the sphere does not appear as an element of the algebra. Not as an element. All right. Okay. So there's 2 lines, and you can rotate around these lines. But these lines are special in that they go through the very center of the sphere. That's what makes it so that you can do ordinary rotations around them. If you try to do a rotation around, let's say I've got a line that's like the following. Suppose you've chosen this line. You want to do a rotation around it. If you try to do that, it will not look like an ordinary rotation. You will be able to get some things to go around it, but remember the rule is that if you're outside the sphere, you stay outside the sphere. If you're inside the sphere, you stay inside the sphere. All of these rotations had the property that, well, if you rotate around something a line that's going through the center of the sphere, then the surface of the sphere, okay, things rotate on the surface of the sphere, but they don't go into, it's not like something going outside will go inside, whereas if you try to do an ordinary rotation around this line, like in Euclidean space, you'd take this thing that's outside the sphere and you'd be able to put it inside the sphere, and that is not allowed. So what happens if you try to do a rotation around this line? And the answer is that you will it'll sort of be like things will bunch up. Things will bunch up such that they stay inside the sphere. There's a plane. And this plane also goes through the center of the sphere. So if you perform a reflection in this plane, it just acts like an ordinary reflection. But if you try to... Okay, note, and it is very important, that this plane meets this sphere in a circle. If I draw another plane sort of up here, if you perform a reflection in this plane, then you'll take everything everything inside the sphere that's on this side of it, which is most of the stuff, will be squashed into that tiny little like cap that you've got there. On the other side, and everything that was on the other side of that, or that was previously squashed into that cap, will end up sort of stretched out, filling up the entirety of the surface of the sphere. This is hyperbolic geometry. What I've just described is reflections in hyperbolic geometry. I'm going to draw an eye. An eye? Yes, an eye. This eye is a very important eye. It's an eye, which is like staring. It's at the North Pole and it's staring downwards, this eye has the following property. The eye can only see things that are on the surface of the sphere. When something touches the surface of the sphere, the eye sees that touch, but it doesn't see the thing itself. When it looks at this plane, what it sees is a circle. In fact, it sees this circle here. And in fact, that plane is E+. That plane is E+. And this plane meets this sphere like this in another circle, because planes always cut spheres in circles. This plane is E1. Because if you perform a reflection in E1, it will look to the eye just like performing a reflection in this line. All right? This plane E1, it passes through the point where the eye is. Sorry. This sphere is kind of the... Like I said, it's not included as an element of the algebra. It's there, you feel its influence in when you look at how things transform in hyperbolic space or under this algebra, but it's not E+. This is E1+, because it's the intersection of E1 and E+ in this space, which looks just like... and if you ask, what does the eye see? What does the eye see when it sees this? The answer is it'll see that place where it pierces the sphere, and it'll see this place where it pierces the sphere. And that will be those guys. That guy, because that is one single algebraic object. In the hyperbolic projective geometric algebra view of conformal geometric algebra, you do get to see that they're connected, because they're a line. E1+ is a line in here, and it's a point pair in here, because it's the place where that line pierces the sphere. You can make objects in a geometric algebra by taking stuff like 0.8. You can add those objects together, and that, well, E1, 2, 3 is the point at the origin, connected to the point at infinity, but you remember that it's that. It's that added to this, so it's like this plane added to this point. They're kind of together, but like these 0.8 and 0.6 tell you that it's more of the plane than it is the point, and that tells you like together these things can form a rotoreflection. So here's the reflection in the plane. It's a point reflection. That's what E1, 2, 3 does, because it's a reflection in those three planes there. And a rotoreflection, which is any time that you have a planar reflection followed by some rotation, a rotoreflection can be somewhere between being a reflection, just a pure reflection, and being a point reflection. And 0.8 E1 plus 0.6 E1, 2, 3 would probably look something like it's definitely more, yeah, it's like this. So I'm not quite at a right angle, but I'm close to a right angle, because I'm closer to being just E1 on its own. All right. So that's about transformations. That's how you add some of these things together. When they're of different grades. Grades being, yeah, whether it's a 1 vector, a 2 vector, a 3 vector, a 4 vector. Yeah, that's the hyperbolic view. The hyperbolic view of conformal geometric algebra. Now, our brains are three-dimensional, if that, really. Our brains are three-dimensional, so, you know, you can use the hyperbolic view to give you insight into two-dimensional conformal geometry, but you can't use the hyperbolic view to give you insight into three-dimensional hyperbolic geometry, except to the extent that you kind of use 2D geometry as a metaphor for 3D geometry. I really mean that. You know, these things are very analogous with one another. You've got, again, reflections in planes, you've got reflections in lines. A plane is not a line, but you can kind of remind yourself of this connection. And when you encounter something in 3D geometry, or if you encounter something in any geometry and you're like, oh gosh, this is really confusing, you can help yourself a lot by saying, what's a simpler version of this thing? And you use 2D geometry as a metaphor, and that lets you go back to the 3D geometry, and then that lets you say, okay, I've got like kind of logical argument for what this thing might mean in 2D geometry. How well does that import to 3D geometry? Maybe sometimes it doesn't. You've got to be very careful about how you import it to 3D geometry, but you usually should be able to do it. But yeah, it's unfortunate we can't see in four-dimensional hyperbolic space, but it is kind of cool how to think about 3D conformal geometry, and which we already have a little bit, thinking about that weird sort of, transformation going around that kind of hoop, the house turning inside out. That's 3D conformal geometry, and it's cool to say, hey, do you know what? You were just thinking about an invariant plane in four-dimensional hyperbolic space and a rotation around that plane. Rotation around a plane doesn't mean anything in three-dimensional space. Rotations are around lines, but there you go. There's an example of how you have now somewhat experienced something that a transformation of four-dimensional hyperbolic space, which is very cool. That blank slate, and we're going to think about the following 2D kind of thing. All right. So here is a circle. Here is a line, and here's a supremely obvious statement. The circle and the line meet at 2 points. Supremely obvious, because I think that statement is pretty much built into your, the nerves in your retina, your visual processing system. There's some bits of geometry that are so fundamental to how the world works that we evolved them into parts of our brain, and that's one of them. But we're going to see some kind of variations of this. Not a line and a circle, but two lines. Well, you might say, hey, they meet at 1 point. And then you could say, oh, hey, how about two parallel lines? They meet nowhere. These appear to be our three situations. But here's another one. You might have a circle and another circle, and these guys don't meet at all. And also you could say a circle and a circle do sometimes meet, but yeah, but that's a special case of this, as we'll see. You want to think about all four of these situations in the view that we just made for ourselves, which is our eye is in three-dimensional space. That's actually a sphere, and it's looking down at some stuff. What do these four situations correspond to in terms of what the eye can see? Well, I guess an easy one would be this guy. So that would be, these two circles will look like, well, yeah, they'll pretty much look like that to the eye. One thing to bear in mind is that as things get kind of closer and closer up to the eye, they kind of become bigger and bigger from the point of view of that eye. That's going to be very important in a moment. I suppose that circle looks a bit small there, so let's adjust the diagram that we've got. I suppose, no, I think that would still be a little bit small. It's somewhat hard to judge these things. It doesn't matter that much. All we're talking about is their contact, let's say. And you can say, hey, well, those two circles don't intersect. But, hey, those two circles don't intersect, but these two planes, where are they going to intersect? Something like, Ooh, ooh, the planes intersect with one another. They intersect in this line. I'm not going to try to take a guess about what the coordinates of that line are, but, you know, I could certainly give them to you if I, well, in some of the conformal, in some of the hyperbolic PGA simulations that I have made. But yeah, so that, I claim that this plane here kind of meets this line. Yeah, that looks pretty good, doesn't it? Kind of goes like that. They meet there. These are planes that are just inside the surface of the sphere, so they've kind of got a bit protruding. What will that look like? That'll look like this, I claim. And these two planes, well, they meet in the line, a line like that. That line meets the surface of the sphere. And so, yeah, the eye can see the place where these two circles, quote unquote, meet. And a reminder that, you know, these lines have sidedness. No, that these lines have sidedness. These circles have sidedness. The arrows are always either going out, all outside or all inside. The conceptually weirdest one will be this one, which we'll get to in a second, but I'll just say, you know, it's super easy. Like, this guy just corresponds to the following situation. You know, you've got your eye again. You should get very used to drawing this picture if you want to do conformal geometric algebra, in my opinion. This guy just corresponds to, hey, I've got a circle this. I've got a circle like this. And both of these are planes. They meet in this line. And that line looks like a point. Or rather, it's a point which, you notice that, hey, we started out by saying, oh, look, a line, a pair of circles meet in, a pair of generalized circles meet at 2 points. They can meet at 2 points. Even in this case, where it appears to be the case that you've only got one meeting point, actually you've got 2 meeting points. It's just that one of them is at infinity. This guy, similarly, and even these two guys kind of meet somewhere. It's not in a place that you can see, but we will have a way of visualizing it shortly. To address this guy, you've got a pair of lines that are parallel, which generalizes in 3 dimensions to a pair of planes that are parallel, so you can use the same logic on that. And that will look like, could have done a worse job there. Alright, I'm going to temporarily draw these planes as being different colors, but just remember that, well, I'm breaking the general rule here. 2 planes meeting each other in a blue line. I think it'll have to do, there's a red circle and a blue circle, and this will look to the eye like red line on the outside, and I've got a blue line that is parallel to it on the inside. Where do these lines meet each other? Well, consider the following. If you imagine yourself, you're looking like a perspective drawing, and, you know, with this picture, let's say you're a person and you're standing up and you're looking downwards. But let's say that instead you then look forwards. What happens when that happens? You see the horizon. You see the horizon. And the horizon is a place where parallel lines can meet each other. These 2 parallel lines can meet, let's say, here. If you've heard me talk about projective geometric algebra, you've heard me say this 1,000 times. And this is one of the ways that projective geometric algebra appears in conformal geometric algebra. So these two lines do in fact meet at a point on the horizon. What's the horizon? Well, do you know what? I've drawn the horizon in black, but I really should have drawn it in, take a guess first, red, because the horizon is a line, just like any other line. This is hopefully the only one vector, let's say, that I'm going to have to draw in non-red. The horizon is a line just like any other. In fact, it turns out that it is precisely this plane at the top here. And it's meeting at a particular point, which I want to draw in green. Yes, I certainly do want to draw it in green. That plane goes by the name E0 if you're doing projective geometric algebra. In conformal geometric algebra, the name it goes by depends on who you listen to. But I don't see anything wrong with still calling it E0. It behaves in exactly the same way. And but an interesting thing is that you can actually rewrite it as E plus E minus. That's E plus, which actually I've already told you. It looks like a circle in conformal geometric algebra. It's the unit circle around the origin. Yeah, so happens. Yeah, and this point here, generates a translation. I'm reminded that this point here is precisely this line here. Things in 2D conformal geometric algebra that generate translations are all these lines up here. They're all lying inside this E0 plane. Yeah, and they all pass through the point here. That's the point at infinity. And one of the sort of weird, annoying things about reading conformal geometric algebra is that people kind of say that, oh, the plane, PGA has the plane at infinity and CGA has the point at infinity, but actually they both have both. Like I say, E0, which is usually the plane at infinity, or the line at infinity in 2D PGA, is E plus E minus in CGA, and the point at infinity is, well, actually, you might be able to figure this out for yourself. The point at infinity in 2D conformal GA is a point in three-dimensional hyperbolic space. This guy is E12, and this guy is E0. This guy, this plane in here that's been a bit obscured is E0. So that point at infinity equals E120. It's equal to E12 plus E12 minus. And E12 plus is here. Should have been able to work that out. E12 minus, well, okay. E12 minus is up there. It's a point that's infinitely far away in hyperbolic space. And so this point is directly in between. If you go infinitely far up in that direction, you get to that point, and that point is E12 minus. We haven't really properly talked about the minuses yet. In 3D hyperbolic space, yeah, you've got these lines, and these lines still deserve markups that look like that. And these points in two-dimensional space, like that one there, they still deserve markup like this, and this one still deserves markup like this, and this one still deserves markup like this. That's just the same sort of thing there. We're just about ready, thank goodness, to talk about how to draw the quote-unquote intersection of this circle and this circle. I mean, they don't intersect is the problem, right? So yeah, now you talk about the intersection of things that don't intersect each other, right? Well, you can still... This might seem like a bit of a hack at first, but it's not a hack. This is... well, it's got a justification in terms of existing hyperbolic geometry, I can assure you. And it also has a justification in terms of, let's say, the philosophy that a transformation should be visualized using the objects that are left invariant by that transformation. They've got these two circles. They have no intersection. But I can still say, hey, what about if I were to perform a reflection in this circle? If I were to reflect everything to the center of this circle, reflect the whole universe to the center of this circle. No, not to the center. Reflect everything that's outside the circle to the inside. Reflect everything that's inside the circle to the outside. So standard inversive geometry. And then do the same thing. And then reflect everything that's outside of this circle, or that has been put to being on the outside of this circle, to the inside of the circle, and then everything that's inside of this circle to the outside of that circle. So, like, you know, to give an example, if you had, like, a thingy here, if you had a thingy, like, that started out here, it would get reflected to being inside this circle, and then it would be reflected to being inside that circle again. It would almost certainly end up in a different place, but that's exactly the thing that we're going to talk about. So that's the kind of transformation that you want to picture now. And that is a transformation. They have no intersection, but they don't define an intersection, but they do define a transformation. And you might say, well, that sounds like a very peculiar transformation. And it is. It's a very peculiar transformation. Let me briefly say a place where other mathematicians would talk about a transformation of this kind. Mathematicians have this thing that they call the Poincaré disk. We're kind of saying, we're briefly talking about everything inside of this box is like proper maths, haha. It's it's mainstream maths. So the Poincaré disk, and it looks like this. You've got a circle, and it's another model of hyperbolic geometry. We've previously talked about the thing, that sort of purple ball that I've been drawing repeatedly is the Klein disk. The Poincaré disk is yet another circle, and it also, like the Klein disk, it lets you think about hyperbolic geometry, but it looks different to the disk part looks same as the Klein disk, but the things that go on inside the Poincaré disk look different to the things that go on inside the Klein disk in particular. So you might have so a line in hyperbolic space In the Klein disk, it looks like a line, but in the Poincaré disk, it looks like a circle. In particular, it looks like a circle which meets the special circle that you've selected at right angles, and it does technically go, in a sense that's relevant to what I think about, it goes outside the circle. But anyway, so yeah, you got this guy as well. So this is a example of a infinitely large circle, and that's perfectly permissible. It corresponds to a straight line, but yeah, this is a large circle in hyperbolic space. I want to do it a little bit better. Right angle, right angle. So that's also kind of a circle. Okay. Circles in the Poincaré disk, or rather, okay, things in hyperbolic space get modeled, lines in hyperbolic space, in 2D hyperbolic space, are modeled using circles that meet this special circle that you've selected in a right angle. Okay. And you can still talk about, hey, I'd like to think about some transformations in hyperbolic space. I'd like to think about intersecting these lines in hyperbolic space to get, points in hyperbolic space. Right. There's some points, and you could think about even rotations. As usual, if you have two straight lines that intersect like here, you could think about a rotation, and that would actually look like an ordinary rotation. It would leave the surface of the Poincaré disk invariant. If you thought about, hey, I actually want to rotate around here, please, what would happen again would be that like everything over here, all of this stuff would end up bunched up around here, and everything that's out there would end up stretched out over to here. People tend to like the Poincaré disk more than the Klein disk. MC Escher, for example, is responsible for, the first pictures of hyperbolic space that I ever saw, which I'm very glad to have seen. And they used the Poincaré disk. The transformations are a bit more sort of readable when you use the Poincaré disk, because it doesn't distort things quite as badly, doesn't bunch things up quite as much. Still bunches things up a lot. I mean, if you think about a thing in hyperbolic space, like here, like that area in hyperbolic space could actually be very, very big, let's say, much bigger than this area here. But, there's no real way for even the best ways of looking at hyperbolic space compromise something. So let's have yet another goddamn model of hyperbolic space, because you haven't heard enough of those. I'm probably not doing myself any favors by calling it that. I mean, of course, Clifford algebra is completely mainstream maths. Conformal transformations is a completely mainstream maths. I mean, the conformal geometric algebra, you could argue, is actually a version of like pentacyclic coordinates, which are a thing that have been around for there's mainstream math. Any mathematician knows the Poincaré disk, and another thing that any mathematician knows is the upper half plane. So here I'm kind of trying to draw like the horizon again, and the upper half plane is another model of hyperbolic space where it's really similar to the Poincaré disk, but you kind of say, well, just to be explicit about it, you take the Poincaré disk, here's my Poincaré disk, and I do this. Here is my hyperbolic space, everything above the line, and you draw like circles They look like that. And they meet this line at right angles, like that. There's my hyperbolic space. Yeah, hyperbolic space is up here, and down here, well, that's not that's sort of outside hyperbolic space, just like here is outside hyperbolic space. And just to say one thing that's pretty important for both the Poincare disk and the Klein ball and the Klein disk, you have transformations of hyperbolic space. You want to think about those transformations. Those transformations, including rotations and translation-like things, will, again, they keep everything that's inside the disk, and they keep everything that's outside the disk, outside the disk. The inside of the disk is, strictly speaking, the thing that's properly hyperbolic space. The stuff that's outside is, I don't know, the shadow realm, which is only determined, like, it's complete. What the stuff that's in it is completely determined by the stuff that's inside hyperbolic space, but it's not hyperbolic space itself. Hyperbolic space is inside the disk. However, there are some transformations of hyperbolic space which do not leave, which like you can ask, hey, can I have like an axis for that transformation? And if you were being very precise, you'd say, aha, well, no, you can't, because you can't necessarily, because an axis, the word axis is associated with the word rotation. A rotation has an axis. Transformations of hyperbolic space, they don't all have axes. Some of them are rotations, and obviously those have axes. And then some of them are kind of a bit like a rotation, kind of like a translation, and those might still have an axis, but that'll just be something which, if you looked at it in the right way, it would still sort of be a rotation. But if you try to broaden generalize the word axis, you say, hey, you know what? If I've got some transformation, the axis is the thing that is left invariant by that transformation. Then you find that every transformation of hyperbolic space does have an axis, and some of those axes are outside of hyperbolic space. I shouldn't have said. I'm sounding a bit like a weirdo if I say the shadow realm. I don't know. I'm sure there's some technical term for the area outside hyperbolic space, but it's perfectly acceptable to think about these axes, and those axes are important to the consideration of the geometry that's inside the disk. I should try to make these pictures a bit more sort of analogous. And these two meet each other here and here, just as these two meet each other here and here. Conformal geometric algebra contains the exact tools that you need to do hyperbolic geometry, and elliptic geometry for that matter, and Euclidean geometry, and scaling. Possibly you've never heard of elliptic geometry, but this is one of the nice things that conformal geometric algebra gives us, and why it lets you make pretty pictures, if nothing else. The only thing that's really geometric algebra about all this is the notation that I'm using. This thing over here, this is a very mainstream math thing to be doing as well. This is just called projective geometry. We're talking about the Poincare disk, and you can say, hey, what does a transformation of hyperbolic space look like in the Poincare disk? Here we've got, ignore what's on the left, please. Here we've got a rotation of the hyperbolic disk, and the Poincare disk, and that is a translation. That's another translation. And you might notice that these translations, which are the interesting ones, they are moving. They're squashing. They're pulling away. So that one pulls away from the left and goes towards the right. There's actually a preserved point pair. Rather suggestive, right? In fact, all hyperbolic transformations have that property in the Poincare disk. Preserved point pair. But it wasn't a point pair that you were going around, okay? It was a point pair that you were pulling away from this one and pushing towards that one. It might also remind you of electromagnetic fields if pair of charges where one is plus and one is negative. We finally get to the punchline. You perform a reflection in this one, followed by a reflection in that one. Bearing in mind the reflections are sort of two-way. They take things that are outside and put them inside, but take things inside and put them outside. But you do two of these. What you will find is that there is a preserved point pair, and it'll be something like here and here. It'll be something like there and there. I don't have a particularly good intuition for that, but I know that it'll be, it'll be sort of like along the line that's like that cuts both of them in half, that kind of thing. And the reason I can be relatively certain about that is because when you do this, you're essentially making yourself a little Poincaré disk. So you do this. It is a Poincaré disk for this pair of circles. It's a Poincaré disk for that pair of circles. But as you can see by the fact that these circles meet it at approximately right angles. If you forget about the circle on the right and consider just the circle on the left, there's nothing special about this point. This point will be sent to somewhere else. Possibly it'll be sent to that exact point there? I don't know. Well, anyway. Yeah, so that's nice, and that gives us a way that we can notate this this point pair, because it's a very different kind of point pair. It's a qualitatively different kind of point pair from the kind of point pair that you would rotate around. These are non-overlapping circles, so they have a qualitatively different kind of point pair. Like, you might say, oh god, why are you spending quite so much time thinking about this, a subtle distinction between these point pairs? Like, one of them you're doing like this, and the other one you're doing like this. Here's what it looks like. You kind of have these arrows going like this. This really looks like an electromagnetic field, right? It's even sort of going along the boundary of the Poincaré disk. Goes like this, goes like this, and it even sort of goes like that, goes off to infinity, comes back around again, of course, because where else are you going to go? And it comes back to it. So this is the preserved point pair, and sometimes, so that's the full markup on it, and to make it a little bit less noisy, you can draw this sort of thing. You're coming out of that one, specifically coming out, and you're going into this one. Why have I drawn those in green? Oh god, I didn't want to draw those in green. That was a bad idea. I care so much about this, I'm afraid to say nothing to be done, because look, green is for trivectors, and this is not about this is not trivectors. This is still a bivector, ladies and gents. Okay, finally, that's bivector, and that's a way of drawing it that's kind of nice. Oh, and you can ask the question, hey, this is kind of, we're talking about something actually useful. I even tried to use this to make a game engine once. What if you have these two circles? Hey, what do those correspond to for our hyperbolic guy? These are two concentric circles. If you reflect in this circle, followed by reflecting in that circle, you will get something like this. It's a scaling. It's a scaling towards the origin, or away from the origin. Though hang on, we've gone back to the hyperbolic picture. These two planes, remember, you have the circles correspond to planes. The planes meet in lines. The lines correspond to point pairs. And what's the line corresponding to this point? What's the line corresponding to this point? Well, look at those two red planes there. Honey, those are parallel. Those are parallel planes. Where do parallel planes meet? you might say they don't meet. So these two planes meet in this circle out here. Circle, the thing is that it's actually a line at infinity. It's a line at infinity in hyperbolic space. It's a line at infinity in hyperbolic space. You might say, oh god. Not only have I got to add a dimension, not only have I got to think of this extra space as being a hyperbolic space, but I've got to think about things at infinity in this space. And once you get used to it, it's really not so bad. It's the case in all of these coordinate systems, basically, that if you want to move away from the origin, you've got to add things that are at infinity. Oh, and, you know, some people who have some small amount of familiarity with hyperbolic space in the Klein disk might look at this and say, no, dude, friggin' the ball itself, this frickin' ball that you've been drawing, that's already at infinity. It's the place that, you know, if you look at pictures of the Klein disk and the Poincare, or even the Poincare disk, things get smaller and smaller. They don't quite reach that, but they approach it, and because that's infinity. There is actually a word for this. The word is, at least according to Henry Segerman, hyper-ideal objects, which is a very weird thing. So what does ideal mean? So this is ideal. Anything at infinity is ideal. This thing I just drew here, which is the intersection of those two parallel planes, it's not supposed to be a circle. It's supposed to be more like the horizon, right? When you're standing on a beach, you're looking at the sea. The it sort of goes on, and you've got the horizon line. The horizon, if you had, you know, a plane here and a plane here, they meet each other at the horizon line. All right. But the horizon line is a line that seems to sort of go all the way around you, so it's kind of like a circle. For the sake of this diagram, we can... so this diagram is cheating now. We haven't been cheating very much until this point, but now we're cheating because we're drawing a line at infinity as a circle. I find it helpful. So that circle is a line at infinity in hyperbolic... not hyperbolic space, but outside of hyperbolic space, because it's beyond infinity in some sense. Henry Segerman is the only one I've seen talking about things this way, but yeah, these things that are outside of the disk itself, for example, lines that are outside the disk and points that are outside of the disk. This one is not outside the disk. This is on the disk. The disk, the sphere. This guy is outside the disk, all right? That one's at infinity as well. At infinity in the Klein disk model of hyperbolic space. Points outside of infinity, what are you going to do? And they get involved in transformations. They are the places where... that line there is a place where, you know, a line and a plane and a plane meet. This point here could be the place where, for example, this line here meets, you know, this plane, right? A point is still a place where a line and a plane meet, and if the line and the plane are parallel so far as you can see, they meet at a point at infinity. The things outside, we call them hyperideal. What about hyperideal planes? For example, yeah, this plane. This plane doesn't meet the sphere anywhere. That is a valid object still in conformal geometric algebra, I'm afraid to say. This is the hardest thing to picture. This is the hardest thing to picture. I mean, it's really easy if you have the hyperbolic view. So it's a plane outside, and it's just a plane there. Very easy to picture. But you can ask the question, what transformation does this plane do? And if you were really naive and you forgot what I said earlier, you might say, God, well, that sounds really weird. Like, it'll surely take everything that's inside, it'll take that sphere and it'll reflect that sphere to being like over here, but that would only happen in Euclidean space, but this is not a Euclidean space, this is a hyperbolic space. And another thing that will be helpful in terms of understanding the coordinates of these planes is that finally, friggin' finally, I can tell you what E minus is. E minus is the plane at infinity in hyperbolic space. Alright? It's this plane, quote unquote plane. A reminder that this plane down here, this plane is E plus, and that will be helpful because we can now label this line as being E plus minus. And E plus minus is a thing that we care about a lot because we were interested in, hey, what if I reflect in this circle and then I reflect further in this circle? And the answer is I scale towards the origin, and that's what E plus minus does, scales towards the origin. Which is to say that the origin is an invariant of the transformation related to E plus minus. Okay. So that point pair is a scaling where it's the point pair somehow with the point of infinity. But you might look at me and say, hey, look. So I was telling you that point pairs, like, let's say you got this point pair. This point pair would correspond to something like this. Right? And it does. This is a different kind of point pair. These guys would do a rotationy transformation, whereas this guy does a scaly kind of transformation, or boosty kind of transformation, or hyperbolic translation Poincaré disk kind of transformation. But that's still the invariant. And for that reason, I introduce the following thing, which I know is once again still fortunately related to mainstream hyperbolic geometry. So here's my my Klein ball. Let's say that you've got like this line here. You do the following, you consider the following. That line has a unique pair of planes which touch the sphere. It's kind of like it's clasping it like this. Alright? Okay, for this line, there's a unique pair of planes that are tangent to that sphere, and there's a pair of points where where they are tangent. The transformation characterized by this line, the 2 points that are preserved by it, are precisely these 2 points. So you've got those 2 points, and so, if you want to visualize this line, which is in fucking 3-dimensional hyperbolic space, we want to visualize it in 2-dimensional space, 2-dimensional relatively ordinary space, you can use that point pair. That's what I'm saying. There's this thing called duality, which I prefer not to rely on too much, but you can use it. So the dual relates any line to it for 3-dimensional hyperbolic space, it relates any line to another line, and it so happens that the dual of this line is this line, which is related to our transformations, because if you wanted to combine a scaling and a rotation, you would be considering a transformation that is characterized in some sense by both of these lines. You'd be rotating around one of them, you'd be scaling in a way that's relating to the other. And I want to briefly mention 3D CGA. You have lines around which you rotate, you have point pairs around which you do weird sort of reflection-y things, but you have another kind of point pair which is actually back to being blue again. It does this kind of transformation. in 3-dimensional space, all right? 3 dimensions of space. The other kind of point pair, it'll reflect you in the sphere that both the points are sitting on, and then it'll rotate you by 180 degrees. That's one way of saying it. So that's a qualitatively different kind of transformation than the blue point pairs. What I'm currently drawing is the 2-vector point pairs. That's a point pair that's a trivector point pair, a green point pair. But there's bivector point pairs as well, which I didn't draw in the very first bunch of pictures. If you had another sphere here, hey, what do I get if I reflect in this one and then reflect in this one? The answer is, in 3-dimensional space, you'd get yourself a point pair that would be something like here and here. They'd definitely be inside the spheres. And those 2 points, they'd be on the surface of another sphere, which would be a kind of Poincaré ball, because it would do hyperbolic geometry but for 3 dimensions using the Poincaré model. If you were to look at what that transformation did to things, it would be sort of like this. Looks so much like a magnetic field. I mean, for God's sakes. And that's qualitatively different from what these guys would do. These guys, for this guy and this guy, because it would rotate you and pull you inwards as well. What does a reflection in 3-dimensional space in E- look like? There is no invariant of this transformation. You can say it's a reflection in a sphere followed by a point reflection. Here's a sphere. If you have something that's like just outside the sphere, well, if it was an ordinary sphere reflection, it would be sent into here, but this is not an ordinary sphere reflection. It'll actually get sent to here, because it's been sent inside this sphere and then it's been reflected across the center of the sphere. So one thing that I was thinking was, I visualized this object as a sphere together with a point. You could say there is something vaguely special about this point, because that is the point which the point at infinity will be sent to by E-. The thing is that it's somewhat subjective which point is the point at infinity. It's just a point that you decided was your favorite point. But you could similarly say E- is kind of like a reflection in this plane followed by one of these in this point pair, which are on either side of the plane. You could say that. You might say, oh, hang on, I thought that we're doing like reflection compositions here, so the transformation you've just described, shouldn't that be, if that sphere is E+, which it is, not E4 but E+, this point is actually E1, 2, 3, because it's paired with the point at infinity. It's that point pair. Shouldn't this transformation be something like E plus 1, 2, 3? And the thing to notice is that E plus 1, 2, 3 is the dual of this guy, because it's got everything in it apart from E-. Transformations and their duals do really similar things. What are you going to do? That's all I have to say about it. I wanted to say about bundles and pencils. This is a line bundle in 2-dimensional space. Line bundle in 3-dimensional space is somewhat different. Say to yourself that this is 2-dimensional space. It's a line bundle in 2-dimensional space, and it's a way that projective geometers, I would say, have talked about what we in 2D projective geometric algebra, we would just call it a 2-vector. So it's this thing that we've been talking about. And it's another way, it's the set of lines through a point. And you can look at a point and say, this point could be a line bundle. And the convention I've been adopting is, bivector points are in blue. So you can look at a blue point and say, yes, it's a line bundle, if it's 2D conformal geometric algebra. Here's a different sort of thing. This is going to be a circle bundle. You can maybe guess what it's going to look like. It's the set of circles through these 2 points. And this looks really similar to this, doesn't it? This point pair was will have been constructed, well, is likely to have been constructed, by taking reflections in these points. So it's really more like, again, the markup is kind of more like this, because you're taking a pair of these circles, you're choosing two of these circles, and you're intersecting them, and you get that point pair. And that happens to be a point pair that'll give you a transformation like this one. And that transformation is different to the transformation that's like this, because this transformation will actually have been made by taking sphere reflections in two spheres that are like this and this. Alright? Or maybe, somewhat suggestively, a sphere like this and a sphere like this. That's a line. In 3 dimensions, you can say, hey, do you know what? I'd like a plane bundle. Set of planes that are through this point. E123 is one of these, because you construct it by reflecting in 3 planes. But when you construct a point pair, let's say by taking the intersection of 2 spheres that are concentric, you get a scaling, and that's that kind of point pair. This is a bundle because it goes through a point in 3-dimensional space. A plane pencil is more like this guy. A set of planes that are through a line. I heard about them from Charles Gunn, and they've been very helpful. I started out thinking, who really cares whether a point pair is a pencil or a bundle? But it really matters. It matters for these. It's what gives you these transformations, and it's the term that we should be using to distinguish these different kinds of object, which are dual to each other. If you want to find consistent terminology, you should look at existing terminology, because you can maybe capitalize on what other people, the amazing things that other people have discovered, and it's also a mark of respect. Like, friggin' hundreds of years of geometers, lots of what they discovered, like, well, it's in rather difficult to read texts, but you should still make an effort to maintain consistency and to appreciate their efforts, and not let it be forgotten. Bundle of planes at a point, pencil of planes at a line. Circle, pencil of spheres. Imagine all of the spheres which pass through that blue circle. That's a sphere pencil. Sphere bundle, it's the set of spheres that pass through 2 specific points. But there was still something missing, and I finally felt like I got it this morning. It's a trivector. It's a line that's in green. Now, if you're keeping track, that's the first time. That should be the first time that I've drawn a line in green. This line is going to be a trivector, and if you are Joan Lazenby, you might be quite happy to hear me say that, because it used to be that people said that lines had to be trivectors in CGA, because CGA was about making spheres and or lines, and if you want, and a line is defined, a circle is defined by 3 points, all right? And if one of those points happens to be, well, if the lines are collinear, then obviously, if the points are collinear, then it's a line by definition. If one of the points is the point at infinity, then it's also guaranteed to be a line, pretty much. So people would say a line or a circle is the join of 3 points, which is true. But if you try to think about transformations, it's relatively hard to reconcile that with everything we know. But I think I've done it now. So when you look at a line, and it's a line that happens to be a line that is a trivector, does make sense from multiple points of view. So here's one point of view. We're going to draw this. So we're going to go back down briefly to 2D CGA land. Remember we had that line and there were two planes tangent to the sphere at 2 points. Also, let's just say if you have a green point outside the sphere, you can have something similar going on where you can consider all the lines that are tangent to the sphere and pass through this point. It'll form a circle, and I'm going to draw this circle very purposefully in green because I'm saying that circle is a way to visualize that line. And I guess to make this diagram a little bit more consistent, I'll draw this point pair in blue. And if we consider what things look like from the point of view of that eye, first of all, you'll have your point pair like this, and it'll be a boosty point pair. Boost being a term from special relativity that's related to this electromagnetism kind of interpretation of these things. This eye will also see big old green circle, but it's a trivector circle. You can have a line in three-dimensional conformal GA, and indeed two-dimensional conformal GA, that is in some sense full of circles. Full of circles, what do I mean? You know, this one will be nice because it's a line rather than a circle, because it passes through our point at infinity. But you know, in order for note that in order to consider this the line, the equivalent point for this circle in hyperbolic space, reminder that this is hyperbolic space over here, you have to eventually make all of these lines meet at a point. That's a point at infinity in the Klein disk model of hyperbolic space. You've got this line, and it's a trivector line, and this trivector line is full of circles. But you don't think about the circles, you think about the line, and you say this line is kind of standing in for all of the circles which are at a right angle to this line. All of these are the circles that are at a right angle to the line, and these lines as well, but a line is a special case of a circle. And that's the claim, and the reason that that's the case is because you can construct this trivector line by taking the intersection of three circles that don't intersect. Similarly, if you're in three-dimensional space, and you take the intersection of spheres that don't intersect, the unique circle passing through them all at right angles. This circle is uniquely defined by these three spheres. And it's able to, having done that, it's able to sort of stand in for all of the spheres. And I don't know of a word for this. I hope that there's some word in projective geometry. Maybe somebody's already coined it, but if people don't have anything, then I'm going to go for it's a kebab. It's a kebab circle, or it's a kebab line. Yeah, because it's poking through the. Yeah. The cool thing is that these circles are precisely, let's say, two-dimensional conformal geometric algebra. These are behaving as boundaries of conformal models of hyperbolic space. Conformal models of hyperbolic space include the things I mentioned earlier, the Poincaré model and the upper half plane model, not the Klein disk model. That is not a conformal model, but these are conformal models, and they can be related to each other, like I said, by doing this. And so it's these conformal models of hyperbolic space, and if you ask, hey, I'm interested in a bound, I've got some sphere or I've got some line or I've got some circle, and I want it to be a boundary for a model of hyperbolic space. Conformal geometric algebra can kind of give that to you. Not a very likely thing to want to do, to be honest with you. People practically always put if you're doing the upper half plane model or the left side model of hyperbolic space, which nobody's, to my knowledge, ever done, you tend to just put the line in the middle and then you're done. You don't want to move the line like this or whatever. But if you're interested in what a geometric behavior of a CGA trivector can be, it's this. The approach to CGA where you build circles out of points is vindicated partly in this view. I mean, everything that I've said up until now has been building, to making, for example, lines out of planes. So making the smaller things out of the bigger things, you might say. Which some people think is backwards. You've kind of got things going backwards and forwards at the same time in CGA. It's a little bit like what Eric Lengel has been doing for a while, trying to think about PGA both backwards and both going up and going down with the anti-product. I wouldn't say it's exactly the same as that. And so I've just said this for hyperbolic space. How about 3D CGA and quad vectors? There are some quad vectors that you might want to visualize. For example, E123 plus E123 minus. The other one that's really important is E0123. It's not a basis quad vector, but the point is that E0123 is the pseudoscalar of PGA, and it can be written as 123 plus E123 minus. Yeah, it's the negative, so there you go. That is the point at infinity, preserved by those guys, preserved by Euclidean transformations, which is the part of conformal geometric algebra that's isomorphic to projective geometric algebra. These guys are quad vectors. How do we visualize them? The answer is we visualize them as spheres and planes. If, for example, E123 minus looks like a Poincaré ball. It's a sphere that's standing in for a family of planes and spheres. Let's have a little bubble coming off it. And they're all at right angles to the surface. All the planes that are involved in the family are going through the center of the Poincaré ball. So, picture just a bubbly ball, a bubbly sphere. That's what the CGA quad vector, this particular CGA quad vector, looks like. I haven't said really how to visualize this guy, but I'm going to point out that if suppose I were to consider the following: E123 minus plus alpha, where alpha is just some scalar, E123 plus. We know how to visualize this guy. This guy is a bit harder to visualize. So if alpha is 0, I've just told you how to visualize this guy. Suppose we slightly increase alpha. What's that going to do? We very slightly increase alpha. That is going to cause our bubbly Poincaré ball to increase alpha. It will grow. If we decrease alpha, it will shrink. We could also, by the way, have thought about a bubbly plane, E23 plus minus, yeah, and it will be covered in these spheres that are all at right angles to the plane, and of course that includes some planes because planes are spheres. Every circle, sphere, whatever that's at a right angle to the thing is included in there. Supposing I took E23 plus, which is that plane, and I take that and I add on some E123 plus. What that'll do is it'll take your plane. Here's your plane. It's currently at the origin. It's dual to the plane E1, by the way, so it's in the same place as the plane E1, but it's a plane that's actually a quad vector and it does very different kinds of transformations. E1 does Euclidean reflection. This does conformal hyperbolic stuff. So if you increase alpha for this expression, it'll take your plane and it will make it go. Here's my plane. It'll go, and it'll shrink towards this point here, which is like 1 unit away in the x direction, or possibly the minus x direction. So it'll go until it shrinks to 0. So that's what it'll do to that plane. If you take E1, 2, 3 minus, and you increase alpha E1, 2, 3 plus on E1, 2, 3 plus, that'll increase the size of your sphere, and make your sphere bigger and bigger and bigger, bigger and bigger, until eventually, when alpha is 1, it will be the sphere is infinity, of course, and that will be the PGA pseudoscalar. This guy. I once did a blog post about trying to visualize that, and I ended up resorting to, you have to go to a higher dimension. But that's not true. You can say, okay, in PGA you've got the one vector E0, and you've got the quad vector E0, 1, 2, 3, and this guy you view as the sphere is infinity, and this guy you also view as the sphere is infinity, but you say to yourself, it's a sphere is infinity that's like bubbly and covered with, or it's like in a cartoon where somebody's just come out of a knife factory and they've got loads of knives going through themselves. Like, it's just, you look up at the sky, which is where the plane of infinity is, and you're like, but I can see like loads of like knives sticking out of it, guillotine blades. Yeah, they're just all sticking there, and that's what that object is. So I've said nothing of E1, 2, 3 plus. That guy is about as difficult as visualizing E minus. In fact, it's dual to E minus, so that tells you what might be going on. Hope that has been enjoyable. See you all later.